Hi guys, I'm just going to talk you through the answer to these questions because part B, it's quite easy, but if it's the first time you've done it, then it can be difficult. So I'll send you the mark scheme as well, but here's the answers. So the exposure of the general public, radiation has changed substantially over the past 100 years. State one source of radiation that's contributed to this change. So it's really important that you state something that wasn't around 100 years ago. So you can't talk about radon gas because that was there 100 years ago. You can't talk about sources in the soil or in food because again that was there 100 years ago. So this is things that we do now that we didn't do then. So the three areas you can talk about, it's only worth 1 mark, so you can just put one of these. You could put nuclear fallout, nuclear testing, nuclear weapons, nuclear accidents, and nuclear waste. You could talk about medical, so you could talk about X-ray, medical tracers, which are where you inject gamma radiation basically and have a PET scan, or a CT scan, which is like multiple X-rays. Or you could say increased amount of exposure to cosmic rays as a result of air travel. Okay, this is the question I wanted to talk to you about. So I'll talk you through it and then I'll show you how I figured it out. So a student measures background radiation of a detector and determines the background radiation as a mean count rate of 40 counts per minute. So that's with no source. She then places an X-ray source 0.15 metres from the detector, so that's the distance. And then she changes it to, she then does a count rate, which is 2050 for that distance. She then changes the distance. So the student then moves the detector further away from the gamma source and records the count rate again. Calculate the average count rate you would expect to see when the source is placed 0.9 metres from the detector. So that's R2. So this is how you need to figure it out. It looks like a long-winded process, but it's quite straightforward. So I will talk you through each stage. First of all, write down what you know. You know the background rate is 40 counts per minute, so it's always going to be that wherever the detector is in the room. The first distance is 0.15 metres and she detects a count rate there of 2050, so I've called that count rate 1. We then, at R2, the second distance is 0.90 metres, so I've recorded that, and then count rate 2 is what we're trying to figure out. So the very first thing you need to do is remove the background count rate because you're going to use an inverse square law, but the background count rate will always stay the same, so it's not subject to that same law. So first thing, remove the background count rate from C1. Okay, so because that doesn't change with distance. What I've done here is I've called that the corrected count rate. That is what it's named. So you're going to do C1 minus CB. So just 2050 minus 40. So that gives you a corrected count rate of 2010. Now corrected count rate is normally given the symbol CO. So I've just called it CO1. So that's the corrected count rate for number 1. Okay. Then we're going to look at the inverse square law. Because it's gamma radiation, it decreases with an inverse square law. So we can say that for the corrected count rate of number 1 is inversely proportional to the distance 1 squared. We also know that count rate number 2, and I should call that corrected count rate number 2, so I'm going to call that CO2, is also proportional to 1 over R2 squared. That means that if I just show you, CO1 R1 squared is equal to a constant. So if I just cross multiply that up there, so we're equal to a constant K. And CO2 R2 squared, so I'm just cross multiplying that up there again, is also equal to a constant. And those constants are the same. So we can put these two terms equal to each other, which is what I've done here. Now we can just substitute in the values. So we've got our corrected count rate number 1, which we just figured out is 2010 here, times R1 squared, so 0.15 squared. And that'll be equal to our corrected count rate number 2, which is something we're trying to figure out, times 0.90 squared, because that's the distance for 2. Rearrange, calculate, you get 55.8 per minute. But this is the corrected count rate, and so that is without the background radiation. So we need to add that background radiation in because that will be the actual count rate that we get, because we're going to get those 40 extra that we had before. So we take it out at the start, do our inverse square law, and then add it back in. Because it's not subject to the inverse square law, we can't include it in this calculation. So we need the actual count rate, so we're going to add on that 40 from before. So we get 55.8 plus 40, which is 95.8, and then to 2 sig fig, that's 96 per minute. Okay, hope that helps.